we present CW Grasp, a framework for generating 3D whole-body grasps with directional controllability. Specifically, given a grasping object, shown in red, placed on a receptacle, shown in yellow, our goal is to generate a body that grasps the object. This is challenging, as the body needs to plausibly reach the object, fingers need to dexterously grasp the object, while hand pose and object pose need to look compatible with each other. To make matters worse, training data sets for 3D whole-body grasps are really scarce. Data scarcity is tackled by the recent Flex method in a divide-and-conquer way. To this end, it first generates a hand grasp via an off-the-shelf method that serves as a guide. Then, it generates 500 initial bodies at random locations and in random poses. However, the guiding hand and initial bodies likely have incompatible directions from which they approach the object, so they both need major post-processing. To this end, for each of the 500 bodies, Flex post-processes the guiding hand to match the body, and the body to match the guiding hand, while preventing penetration with the receptacle. This often produces unrealistic body poses or fingers that miss contacting the object, because major post-processing takes place too late. We tackle this with a novel method called CW Grasp. Our key idea is to perform local scene reasoning early on instead of too late, so that we generate already compatible guiding hands and bodies that need only small refinement instead of major post-processing. CW Grasp consists of 3 novel models, namely Reaching Field, C-Grasp, and C-Reach. Reaching Field is a probabilistic 3D vector field that encodes the directions from which a body's arm and hand can reach an object without penetrating the supporter receptacle. To build this, we take the following steps. First, we sample points on a sphere around the object and shoot rays from the object's centroid to these points. Then, we discard rays intersecting with the receptacle, shown here with red color. However, not all remaining rays allow a body to easily approach the object due to the receptacle's geometry. For example, if a person approaches the sofa from the back, the sofa's backrest obstructs easy access to the object. To tackle this, we project the remaining rays onto a horizontal plane parallel to the ground and discard those that intersect with the receptacle, shown here with red color. However, to grasp an object, a body needs to stand at a nearby place on the ground without penetrating any occluders. To find such places, we traverse the remaining rays while shooting new vertical rays to the ground, and in case these intersect with any occluder object, the parent ray gets discarded. Still, all remaining rays are infinitesimally thin, so they ignore that a body and its arms have a certain volume, which might cause penetrations with the receptacle. To resolve this, we swipe all rays within a small range around the vertical axis, and discard rays intersecting with the receptacle. The final remaining rays form a reaching field by assigning a likelihood to each ray depending on both the object's height and the ray's direction. Here the likelihood is shown color-coded. Red denotes a high likelihood and blue a low one. For example, objects near the ground are likely grasped from higher above, while objects high above the ground are likely grasped from below. In test time, sampling reaching field produces a vector denoting a likely reaching direction. Importantly, we draw just one sample from reaching field, and condition on this the other modules of CW Grasp, namely C-Grasp and C-Reach. Then C-Grasp generates a guiding hand that grasps the given 3D object, with a palm direction that agrees with the conditioning direction. Similarly, C-Reach generates a body that reaches a given 3D point, which in test time is the object's centroid, with an arm direction that agrees with the conditioning direction. Note that conditioning C-Reach and C-Grasp on the same direction produces a reaching body and guiding hand that are already compatible with each other. Therefore, unlike Flex, we keep the guiding hand fixed and only need to optimize the body so that its hand matches the vertices of the guiding hand. Note that our method works even with just one body sample, while Flex requires 500 samples and conducts major post-processing for all these. Therefore, our method is 16 times faster. We perform a qualitative comparison between CW Grasp and Flex. CW Grasp produces whole-body grasps that look more natural than Flex. We show examples where objects are placed at different height positions, ranging from very low to very high positions. Flex often generates bodies with unnatural poses, sometimes not even facing the object, or with hands that miss touching the object. In contrast, CW Grasp produces much more realistic bodies and grasps. To evaluate the perceived realism of these, we conduct a perceptual study. In particular, we apply both CW grasp and flex on the same scene configurations and render the produced grasps in a whole-body view and a zoomed-in view of the hand and object. Each example is shown to 35 participants, who choose which method generates the best result in terms of natural body pose, realistic hand grasp, and overall interactions. CW grasp is preferred 70.8% of the time considering the full-body view, 71.6% of the time considering the zoomed-in view, and 71.23% of the time considering both views. Therefore, CW grasp produces grasps that are perceived as significantly more realistic, while requiring 500 less body samples and runs 16 times faster. As a closing remark, note that CW grasp can uniquely generate both right and left-hand grasps. We show examples of left-hand grasps here. For more details, please visit our website. Thank you for watching.